Welcome all to the AI Consortium speaker series. Today we have Dr. Krishnan joining us. This is a special session mainly because Dr. Krishnan is leading one of the AI thrusts, the trustworthy AI within the Matrix Consortium. And Dr. Krishnan has been an associate professor in the electrical and computer engineering at UTSA, and he also holds the Microsoft President's Endowed Professorship. Dr. Krishnan received his bachelor's in computer science from Pondicherry University and master's in computer engineering from NJIT and PhD in computer science from George Mason. His current research interests are in applying machine learning to strengthen cybersecurity of complex systems and developing novel techniques to address security and privacy concerns in machine learning. He has won several awards, including the NSF Career Award and University of Texas System Region's Outstanding Teaching Award and the President's Distinguished Award for Research Achievement. So let's give a warm welcome to Dr. Krishnan. I guess the virtual claps.
Thank you. Thank you. I'll take what I can get in a virtual setting. But thanks, Dirisha, for the kind introduction. I guess we could get started.
Yes.
Okay. All right. So one last time, can everyone see my screen? I don't want to be speaking to an empty screen.
Yes, we can.
Okay. Excellent. Thank you. Okay. Morning, everyone. Thanks for joining this talk on a Friday morning. This is a app, Dirisha mentioned about 2 tracks of research that I'm interested in. So this concerns the first track, which is in the business of exploring different kinds of machine learning techniques that could be used for improving cybersecurity and privacy of systems. I also do some work on foundational aspects of machine learning, but those are a little bit on the early stages. So I thought I'll give you some view on the first part where I've done a lot more work. And I selected one topic in that front, which concerns using machine learning for malware detection. And in particular, this work and this talk is going to focus on using deep learning techniques such as convolutional neural networks for malware detection in cloud computing systems, in particular infrastructure as a service cloud. So let me go through this, and if you have any questions, you can stop me anytime. Keep it interactive if you would like, and you don't have to wait until the end. If I don't respond to your chat, please just unmute yourselves and shout. That's fine. Okay, let's get started. So the first, I just want to establish a baseline. So if it's too elementary, please bear with me for 2 slides. So the first business is I want to establish what cloud is and what particularly infrastructure as a cloud is. And this is the National Institutes for Standards Technology's definition of cloud, which has sort of become the de facto definition of cloud. So it's just a 1-page document if you have not seen it. So I would highly encourage for those who are not familiar. But basically the cloud is supposed to have different kinds of characteristics. And some of these characteristics would make sense to you now, because if you're thinking about a cloud, we are talking about resource pooling, right? That is pooling a bunch of resources together across different customers, right? Different tenants. You have measured service. So you have a pay-as-you-go kind of a approach where you pay what you use for. So if you have a whole server and you don't use the whole server, you only use the part of the server, you just pay for it, right? Network access. So resources are available via network access. And on-demand service, as and when you need a machine or some kind of compute resource or network resource, you get to create it and you get to get rid of it the moment you don't need it. The most important and interesting characteristic of cloud is the rapid elasticity. Just want to make sure, can you see my mouse? Okay, all right, so rapid elasticity. So that essentially concerns the aspect of auto scaling, right? So essentially when there is demand, you can increase the number of compute infrastructure or network infrastructure, storage infrastructure, whatever you want. You're able to elastically sort of expand and then contract depending on the demand. And that was the killer aspect of cloud. But it turns out when you're talking about a cloud computing platform, there are all kinds of interesting vulnerabilities that are carried over from pre-cloud era, if you will, right? So there are standard vulnerabilities that are out there, but then because of certain natures of cloud, it turns out it also introduces some interesting new vulnerabilities that are not very common in the past. So this talk, in this talk, I would like to focus on this key question: can we leverage cloud characteristics, such as the ones that you see in those green bubbles, for online malware detection? I'll define what is online malware detection. I'm sure you all know what is malware detection. And in particular, toward the end of this talk, I'll show you how we sort of, build on the auto-scaling capability of a cloud computing platform for this purpose, okay? Now, here is a classic picture of what we call as OpenStack, a open source platform for cloud computing. The gorilla in this arena is, of course, Amazon, Microsoft, etc. But this is an open source software developed locally here in, at least founded locally here in San Antonio by Rackspace and others, but developed globally, right? So this is an open source initiative. And OpenStack is an infrastructure as a service cloud. I'm sure some people will disagree with that. At least it started off as an infrastructure as a service cloud. And the idea here is that you're able to create different kinds of virtualized hardware resources on the fly, such as virtual machines, containers, virtual switches and networks, virtual storage. So as and when a particular customer could be a single person, or it could be a whole organization such as Netflix. And whenever they need to create a VM, they are able to just create that machine and deploy different kinds of services on it and expose it to their customers. And I'm not doing justice to OpenStack, so this is just a brief overview of what it is. And if you have any questions about what IaaS is, and if you're not familiar, please feel free to ask me. But the rest of the talk is going to be dependent on that, right? So basically, you're able to get access to virtualized resources on the fly, especially compute and network. All right, so the problem statement then again is, how do we leverage cloud characteristics for effective online malware detection? Okay, so those cloud characteristics that we saw in the first slide. Okay. So the key characteristic that I'm going to focus on in this talk, there are other aspects we could focus as well, but in this talk, I want to focus on auto-scaling, and I want to see how we can actually leverage the aspect of auto-scaling for malware detection. Okay, now then all that's left to do before I get into the details of this talk is to explain what is online malware detection for those that are not familiar. So you can sort of broadly classify malware detection using machine learning into two different paths, types of work. Pretty much the entire literature could be classified into these broad categories. On the right-hand side, you see what we call as file classification. Here, the assumption is you have access to the malware file, right? So the executable, if you will. So I got access to it, and you don't know whether that is malware or not. So I need to analyze this program, whether that is a source code or it is in binary format. I want to analyze it in order to understand whether this piece of software exhibits malicious behavior, right? And there are two standard techniques, and of course there are other techniques, hybrid of these two techniques, but one we call as static techniques, static analysis, and other is dynamic analysis. And the distinguishing factor here is that in static analysis, I never run the program, I simply analyze. It's a passive analysis technique. I just observe the code. I use some kind of programming technique to go through the code and try to figure out what it's doing. In the case of dynamic analysis, I run that code and see what it does, right? It has its pros and cons in each of those cases. There are certain bugs that are very difficult to catch in static analysis that you can catch in dynamic analysis, and vice versa, okay? And at the bottom, you see various kinds of features that we typically extract in order to perform these kinds of analysis. One of the couple of most popular techniques here includes control flow graphs. So you see, who's calling who, you build a complex graph, and then you try to fingerprint a particular sequence of calls in order to understand whether that is malicious behavior or not. Now there is binary engrams. So this is essentially taking your source code or binary code and then splitting that into different engrams and then trying to compare and see whether you can flag a malicious sequence of engrams, if you will, right? And etc. On the left-hand side are different kinds of features that we use for dynamic analysis, such as performance metrics, right? So these are things like CPU utilization, memory utilization, etc. So what makes online malware detection different from a standard technique of file classification? In the case of online malware detection, we do not look at the actual file because, although it has its benefits, most of the times what happens is, hey, I have a running system in my organization or enterprise. I want to know whether that system is having holds a malware in it, okay? Welcome to my old phones here. Anyway, so I want to see by just observing the system behavior, I want to see if it's exhibiting any kind of malicious behavior, right? I don't know the actual file that is actually a malware. So that is what makes online malware detection interesting and different from a traditional approach of file classification. So at the bottom of the slide, you can see what I mean. You know, most, if not all, cloud malware detection research simply focus on restricting those features to those only fetched through the hypervisor, but they rarely benefit from cloud characteristics. Okay. All right, so here's a classic example of certain kinds of reference architectures that Amazon has put forth. All right, so this has been maybe a couple of years old architecture, but I'm sure the underlying theme holds still. Basically, this is a standard web hosting architecture, right? So you have 3 tiers. So at the in the front you have a load balancer right here. And then you have a auto-scaling web servers. You see that horizontal arrow, that the load balancer distributes the load depending on how much traffic you're seeing across many different web servers. And this is auto-scaling because the number of web servers expands and contracts depending on the demand. And then you have another elastic load balancer here in the middle. And then you have the application layer, which is a set of application servers, once again, that is load balanced. It expands and contracts depending on demand. And in the very back, you have your database servers. And typically, we do not scale database servers because you might deal with inconsistencies and so on. So you simply replicate it oftentimes once in a while. Okay, so for this talk, we will not worry about these database servers and handling those database issues, but let's focus on the compute here, such as web servers and app servers that are auto-scaling in an enterprise setting. Okay, so the Amazon has different kinds of reference architectures such as these. This is an example for web hosting, and they have things like log server analysis, Hadoop, et cetera, right? Okay, so this work focuses on collecting different kinds of features from these kinds of virtual infrastructures such as web servers, application servers, in order to detect malicious behavior. So I'm going to lay out my talk into 3 different sections, as you see here. Let's start from the top and we'll go clockwise. And at the top, we have black box features for multiple VMs. So imagine you have multiple VMs, such as these web servers here, or these application servers here, right? And my first problem that we wanted to explore was, can we extract certain kinds of black box features, meaning we do not look into the VM, we look outside the VM, right? So think of VM as a machine. I'm just going to look at the behavior of the machine by just observing it externally and collect different kinds of features. And the kind of features we're talking about are things like CPU utilization, memory utilization, network. There's a wide array of 30 plus different features that are available that we could collect. And that is what I mean by black box features across multiple VMs. And then we went into this topic of, can we now strengthen that? Black box has its limitations. Can we then strengthen that by doing some white box feature extraction across single VM and then subsequently across multiple VMs? And can we use all of these features and apply some kind of machine learning techniques in some innovative ways in order to detect malware? So that is going to be the rough outline of how I'm going to progress for the rest of this talk. And as you can see, if you see the dark green arrow, I'm not sure what colors you're seeing there, but if you see the inner arrow that goes clockwise, that is from black box to white box, typically one would agree that improves the detection ability of your system, right? So the more inspection I can perform on a virtual resource, the better I can detect a malicious piece of software, right? Or something that is malicious executing in your system. But at the same time, the more in-depth I go and the more data I dig, the practicality is challenged, right? Because it's pretty expensive. Remember, we are talking about some serious scale here, right? So think about Amazon and Amazon catering to all of its customers. Think about running some white box collection mechanism across their customers. It's pretty darn expensive, right? So it becomes, you have to strike a delicate balance between these two, right? So we might very well wish we just have white box features across multiple VMs all the time, but many times we may not. That's the reason we sort of explore both black box and white box features here, okay? And let's start with the black box features for multiple VMs. So, I'm going to give you a very brief overview of 3 different works, actually many different works, but the main works are the 3 that I'm going to talk about. And this one was performed and it was published in IEEE Cloud Computing a couple of years ago. If you're interested, you can take a look. And here's the key observation for this particular work. Okay, and now I want you to keep in mind this reference architecture that we talked about here, right? So just for the sake of explanation, I'm going to consult this reference architecture. So in particular, I want you to keep track of these web servers and these application servers, and maybe even just focus on one tier here, right? So let's just look at this application server, for example, that is auto scaling. Okay, so the key observation here is that if you have a set of virtual machines for application servers, those VMs that are performing the same function should behave similarly. Remember, we're talking about auto scaling, right? Meaning every VM in that particular tier of application server is exactly a copy, right? So those computes are created from exactly the same copy, same image, and therefore, and it's processing a very similar set of workloads. And therefore, those VMs ought to behave similarly, and similarly is in quotes, okay? So they don't have same behavior, they got to have similar behavior. So that hence you need some kind of statistical techniques, right? To sort of formalize what that similarity is, and hence we bring in machine learning techniques here. And the first approach we took was very, very simple approach, just do some basic clustering, right? KNN kind of approach. And here's the idea, right? So if you can find 3 different clusters in a given web, 3-tier web architecture, right? So, I'm just informally, I'm calling these different clusters as blue, red, and green. And imagine, given a set of VMs, you are able to put them in one of these clusters, right? So going back to the previous picture, you have a web server cluster, you have an application server cluster, let's say, imagine that's red, and you have a green cluster, imagine that's some other tier. And in this, I know I told you there is no database, but imagine that's a database tier, okay? And here are some examples on the left that shows you how we can sort of characterize that cluster. Imagine these VMs, these orange thingies inside these cloud bubbles, are created during a certain time frame, has a certain kind of network profile, has a certain kind of memory profile, also has a certain kind of disk IOPS profile, right? So I'm sure you will agree that a web server tier behaves collectively differently from an application server tier because the nature of the workloads that they process are different, right? So there's got to be some uniformity among the VMs in each of those tiers. So now, when you're dealing with auto scaling, on the right-hand side, a new VM gets created in a cloud environment, okay? And we want to understand if that VM is a malicious VM or not, right? If some hacker got into the system, is creating a bunch of VMs, and then they are able to launch different kinds of denial of service attacks across the internet, right? So that's what we want to find out. And the question is, or ransomware attacks, right? So the question is, a new VM is created, does it belong to one of these 3 clusters that I already know should exist, right? So imagine this VM's creation time is 9 a.m. and it has a network profile, whatever. So let's say you measure these things for a small period of time, and very quickly, I want to fit this particular VM in one of these clusters. Right, that's the question. I'm simplifying a lot of these things here. The creation, these metrics don't look as simple as these. These are very complex metrics that we have multidimensional metrics, etc. Okay, so that is that. The question then here is, given a VM, does it fit in one of these clusters? If not, we're going to declare that there is something seriously wrong with this VM, right? There's something anomalous about this VM. That's essentially what we're going to say. So here's was there a question?
Sorry, there's a question in the chat.
Oh, sure.
Someone wanted to know, what is the key difference between the black box and white box features? Does white box mean getting access to the actual data on the Elastic, on the EC2s?
White box simply means, black box simply means observing metrics that can be collected without entering the VM. Right? So can I just collect some metrics from just observing the VM as a black box? White box means, can I actually look into the VM and collect some metrics from inside the VM? It's more intrusive, if you will, right? So if you're a customer who's running a VM on Amazon Cloud, you probably do not want Amazon to poke into your VM, right? So it's a lot more intrusive. But if you give me some insights on your VM, I can probably provide you better service in malware detection. Right. So when we get to the actual metrics, I'm sure you'll, just bear with me for a couple more slides. You will see what I mean by black box versus white box.
Okay, thank you.
Okay, thanks. All right, so so here's a cluster mapping, right? So imagine 2 different graphs. Again, this is not a real, this is just made up graph. for CPU utilization and memory utilization, right? So let's say you have a bunch of VMs, VM1 to VM4, and you're able to fingerprint and cluster these VMs. So you can see that VMs 1 and 2 follow a similar pattern, right? So these are auto-scaling, let's say, web server VMs. They're following similar pattern, and they form a single cluster. And similarly, you have the green VMs, VM3 and VM4, and you can see that they are following somewhat similar features, and therefore they form a separate cluster. And imagine that's the applications cluster. And you have similar graphs you can draw for various different metrics that we could collect. Remember, this is what we mean by black box metrics. So I can simply look at the CPU utilization of a given VM without having to look into the VM, right? So I can also look at memory utilization. I can have 30 plus different metrics I could collect for a single VM, right? So it's a lot of data we could collect. And the question is, there you go. That is a VM5 that came into being. And we want to see if that VM's behavior is significantly different from known behaviors of VMs, right? And in this particular example, you have a suspicious VM5 in terms of both CPU utilization, memory utilization, etc. Right? I know many of you are already thinking, hey, it's not that hard. VM5 can actually simply try to mimic VM1 and VM2, right? And somehow try to hide. And that's where collecting deep set of features helps, right? I'm not here to suggest that we can detect all kinds of attacks, right? If there is a malware and advanced persistent threat that's going to sit around for a long time doing nothing, and then once in a while it's going to sort of launch a serious attack. Yeah, this technique right now, it's not going to help to detect those kinds of bugs. Okay, so those are serious problems, I understand, but you'll be surprised. A vast majority of attacks that occur on the internet today can be detected using very if you collect detailed set of features, and if you're able to identify different clusters, you will be able to detect. In particular, for instance, the Atlanta airport attack that occurred a couple of years ago. No battery. If I can shut this thing down. Sorry. Okay, if that particular attack was actually a ransomware attack, as you probably are familiar, right? And it turns out, if we had a technique like this in place, right, to detect ransomwares, I'll show you some workload experimentation that a little bit later, but you'll see that it's fairly easy to detect, and you didn't have to shut down one of the busiest airports in the country, right, for this. Okay, so here are the clusters, right? So for that particular architecture, imagine you're a tenant and you're using Amazon Web Services, and let's say you have 3 tiers, right? So you have web server auto-scaling tier, app server auto-scaling tier. Ignore the database servers for now. So these are the different clusters. So for this particular organization that used a web application hosting service from Amazon, they would have 2 different clusters, a web cluster and an application cluster. And anytime a VM is created, my goal is to fit it in one of these clusters, all right? So here are some examples of VM features, black box features that could be collected, right? So there was a question about what are black box features. So here is an example of set of features, but there's a lot more, right? So if you're using OpenStack, and for those who are familiar, you have a service called Ceilometer. Essentially, that's the metrics service that collects all kinds of metrics about a given VM. And these are available through an API call. For those who are familiar with things like Amazon Web Services, they used to have something called a Cloud Watch, which is essentially watching and observing the entire cloud. And you can collect all kinds of interesting metrics about a given VM and given switch, given storage, right? All kinds of resources out there. And these are some examples, right? So CPU utilization, memory, disk read, write. So think about, you have 30 plus different features, right, that are collected across a VM. And you can actually apply some kind of serious machine learning techniques on this data set in order to profile what is good and what's bad, okay? And here's the experimental setup we did on OpenStack. So we had you can see from the top, we simulated a bunch of clients, right? And we had a load balancer. We essentially simulated the reference architecture for 3-tier web application that Amazon has, but we did it on our local cloud in UTSA, and we had an auto-scaling web server using Apache. We had a load balancer again, and then we had an auto-scaling application server where we run a very simple application such as WordPress, right? So imagine for maintaining websites and so on. And we simulated all kinds of client requests from the internet. And at the back end, we had the data stored in a database server. And we generated traffic manually using many different types of distributions. So Poisson versus on-off path 2, which is more closer to internet traffic, right? So we distributed across, we generated these kinds of traffics. And we apply different kinds of clustering techniques. And I just want to show you for one simple clustering technique here, which is a sequential k-means for clustering. And we had 50 different clients we simulated, and we had 3,600 requests per hour. Okay, and we simulated different kinds of requests, gets and posts, right? So these are for websites, and we collected all the data. So here is how we collect the data. Well, maybe for the next one, I'll show you how we collected the data. But essentially, we collected all of these metrics, right? As the system is working, we collected all of these metrics and we ran clustering on it, and we simulated some ransomwares, so real-world ransomware such as kill disk, etc. Okay, so this is I'm just going to show you for one example of a ransomware, but we simulated a whole bunch of ransomwares for 2 different distributions here, and you can see that if you try to cluster it, and if you try to fit a VM in a particular cluster, our performance actually for detecting a kill disk, which is, I know it's a giveaway, it's a fairly simple ransomware, it suddenly increases all kinds of utilization, right, out of whack, right? It just goes completely out of whack. And immediately you can tell what is what, right? And you know that ransomware is one of the most popular types of malwares on the internet today, right? So there's some study that says more than 40% of cloud malware types are actually ransomware deliveries. I actually wanted to show you a video, maybe instead of time. Essentially, that video simulates this attack at runtime, right? So it goes from initial VM creation all the way to a malware injection point and then detection point, right? So you will see the curves developing on the go. Or maybe, what the hell, I'll stop early if needed, but let me try to show that, okay? Let me see if I can.
A question, Ram.
Sure.
How is malware detection on the cloud different from the detection on the host?
Right. So excellent question. That's essentially why we are focusing on cloud-specific features, right? So in particular, we are looking at auto scaling. Yes, right now I have not answered that question, so bear with me toward, when I get to the next couple of couple of slides a little bit down the line, you will see how we are actually exploiting auto scaling features in order to detect a malware. Okay. All right. Can you see this video right now?
Yes.
Okay. All right. So hide this. There we go. Okay. So this is a simulation. This is data live collected from. It's not live now. We have recorded it, so I don't want to do live demo. But this is data that is being collected as and when the system is running. So we have a 3-tier architecture that is running. And on the left-hand side, you can just pay attention to the left-hand side in the interest of time. And you can see that different charts are being shown here as and when we create. Yeah.
It's not playing yet?
Oh, I haven't played yet, sorry.
Okay.
Yeah, it's on pause. So you can just pay attention to the left-hand side and you see that you have one graph for CPU utilization, one for memory, and then 2 at the top for disks, right? And you see different shapes and colors for different types of clusters that we are trying to create here. Right, so a diamond shape versus a square shape, etc. As it shows, and the circles shows for different kind of clusters, and each color indicates multiple copies, right? So as and when a new VM gets created, we try to do that. All right, here we go. So take a look at the thing on the left-hand side, and it's going to keep building this graph as and when new data is being collected and analyzed by clustering algorithms. And you see already 3 clusters getting formed, right, within a few seconds, and clusters will stabilize. And very soon what we do is we inject a malware in one of the VMs, right? So we inject a ransomware, a real world ransomware in one of the VMs, and that is the red, right? And you can see that its profile starts to completely diverge from the rest of the clusters. And at that point, it's an administrative decision that needs to be made. When is the right time to actually say, raise a flag, an alarm, right? That there is something malicious that's going on right there. And you can see that CPU utilization and the memory resident starts to be complete. Its profile starts to be very different, which is in red, right? Completely different from rest of the clusters there, okay? All right, okay. I'm gonna share the screen again.
A quick question on the accuracies that you've shown on that plot, Ram.
Sure. Is my slide visible now, or should I?
Not yet.
Okay, there we go. Here we go.
Yes. So I see that the accuracies for the Poisson distribution versus this on-off Pareto are quite different.
Right.
So at what time or what would be the right call for someone to make based on this level of accuracy, right?
Yeah, so I don't know. It's very hard, right? So this is where the human has to jump in and determine what is the right time. And I think for this talk, and because we are talking about internet, we can focus on the chart on the right, which is more closer to an internet traffic. It's well studied that Poisson is not an internet traffic. So you can look at on-off path too. And of course, at some point, and you can see on the x-axis, there are different window sizes. So we don't want to, every time a new sample is collected, a sample essentially is a sequence of metrics that I've collected for a single VM. You don't want to make a decision right then. You're going to get a lot of false positives, right? So that's why I have a window size on the x-axis. So we collect 40 different samples, right, over a certain time, 50 different samples over a certain time, right? So with different frequency, et cetera. And you have to determine what is probably the best window for your particular application, right? What makes sense for WordPress probably is not going to be good enough for some other application server. Right?
So you need some kind of adaptive window size then.
Absolutely, absolutely. It's all toward the end. I'll say I'm going to hand off and say this is all future work, right? Okay. All right. So I can't move.
I think as you're figuring that out, there was one more question from the chat window. Is it possible to detect kernel level rootkit that simply modify the data structure to hide the process or module?
Not in this work, right? Unless the kernel level rootkit is going to do something that's going to appear at the metrics level. So make sure I can. Okay, finally my screen is moving. Yeah, so rootkits are a different game, right? So if depending on the nature of the rootkits, we haven't experimented with rootkits in this particular work, but depending on, once again, the pros and cons of this work pretty clearly just from the kind of metrics we are dealing with here, right, at black box level. So obviously there are certain kinds of malwares that we cannot detect. There's absolutely no question about it, right? And there are other works to detect, rootkits, right? So in security, often you will see that there's no single work that's going to claim that, oh yeah, we can detect all malwares. No, you should run away from the talk if anyone claims that, right? So most of the times what's going to happen is we look at a particular kind of malware or a malware that exhibits certain kinds of issues and then see whether you can actually try and capture it. And that is not to say that other works are not important. There are zero-day attacks that are critical, that makes it very hard to detect, et cetera. There are challenging works there. But that is not what this work is focusing on. Okay, all right. So now let's focus on some, I'm going to show you a couple of examples on white box level features, and it's going to follow the same approach here. And the main difference between the previous one and the next one here. So for now, in this particular, the next section, I'm going to focus on a single VM for a moment. Okay, before I get into that question of how do you deal with multiple VMs in white box, let's focus on a single VM and let's see what kind of white box features we can collect on a single VM. And here are, once again, these are just examples, but there are 28 different process level metrics that are available in Ceilometer in OpenStack. The reason we deal with OpenStack is it's probably the only mature enough OpenStack platform that's available, cloud computing platform that's available for us to play with. We can't do this on it's much more difficult to do this on Amazon. We could run the experiment, but we might be violating the terms of service if we inject malware on Amazon Cloud, right? So probably not a good idea. So we stayed away from that. But it took a lot of work to inject malware in UTSA Cloud, okay? So it took about a year to get the process through. But eventually we got our own network that is isolated from the rest of UTSA network. And then we inject all kinds of malware in there right now. But so we collect 28 different process level metrics. Here are some examples of metrics. And the key word here is process level metrics as opposed to VM level metrics. And that's what makes this white box, right? So imagine a Linux kernel or Linux machine with all kinds of applications installed. And it probably has hundreds of processes, right, running at any given time. And if you press Control Alt Del in Windows and look at the taskbar, you see all the processes there, right? So that's what I'm talking about, all those processes that are running in the system. And what we do is we take each one of those processes, right, and we collect 28, I mean, I forgot exactly, but this is in one of the papers. In another paper, we collect a lot more data. But essentially, we collect a bunch of metrics for each one of those processes. And we then now try to see whether there is some kind of process level anomalous behavior when there is a malware in that particular VM versus not, right? That is the key question we're trying to answer here. And as you can see, here is, here is an example of a sample on the right-hand side. XT is one sample that is collected at time T. And the rows are various processes. So we have, imagine there are M processes here. So we have P1 to PM. And the columns are features, right? So these are things like CPU utilization for process one, memory utilization for process one, number of context switches for process one, etc. How much time it has been running, that's for process one, etc. So N features for M different processes. And that's one sample. In fact, what we actually do is, we actually call it 3D CNN simply because we don't want to be dependent on a single time, because that is going to lead to a lot of false positives. So what we want is to collect a bunch of these samples together. And so that's why you see a cube here, right? So the third dimension here is the time. So we collect a bunch of these samples together and club them together, and we call that as a single sample. A single white box sample across many features, across many processes. And we collect this over a period of time. And then we use CNN to actually analyze if there is any kind of malicious behavior. Okay, so here's experimentations. Oh, before I go there, one of my students, Randy Klepetko, he actually got onto this problem, which is when you're dealing with non-natural data, right? So typically you will imagine that CNN, the classic use case is images, right? So in images, the data is given, right? So you can imagine God-given, right? So essentially you take a picture and that's there, right? There is no changing that in some sense. I know you can play with the intensity level of pixels, etc. But in general, the structure of the image is essentially represented in the natural world. And there is no question of ordering the pixels in any particular order or not. But when you're dealing with non-natural data, such as malware data here, this particular kind of sample, the key question becomes, should I order the process as P1 to PM, or should I have a different order, right? Similarly, in what order should I place these features? Should I place F1 before F2, or in what order, right? So if you have N features, you have so many, and M processes, you have so many different orders in which you can configure a single sample. And it turns out that depending on what order you configure those samples, when you're running CNN, the performance can have a significant impact. That's very interesting result, right? So because typically you wouldn't think of an order problem when you're dealing with images, but when you're dealing with non-images or non-natural data, where the order is not dictated by the natural world, you have the option of playing with that order. And it turns out, depending on what order you play with, you have different results. And I'm not going to go over all these charts, but essentially what Randy found out was, here's the red chart here. He tried different column ordering. He simulated a large number of column orderings, and he simulated a large number of row orderings. And then he found out that different kinds of orders have different interesting behaviors in terms of malware detection ability. And here is an example. This is the previous result one of my previous students actually worked on. And this is the AUC. And here's what he found out if you just did a random ordering, which is crazy, right? So you just randomly order it, and it turns out it has better performance. So that started, and then he found out that if you actually correlated certain columns together, you would imagine that whenever, let's say, a CPU utilization goes out, maybe memory utilization also goes out correlated with each other, right? Then you put those two columns together, right? So he found out that certain kinds of columns could be correlated, and therefore he placed those columns one after the other, close to each other. And then he found out that certain kinds of orderings had better results than a random ordering, and in particular, the old ordering that the previous work did. Okay, so that's, and he also tried different kinds of row ordering, and there are some interesting results there. If you're interested, you can take a look at this paper at the bottom here. Okay, and if you're interested, I can send the slides out and you can have access. Okay, and here's the experimental setup for this particular white box work. And once again, we had the same setup. We had a 3-tier web app architecture. So we have different clients, a web server, auto-scaling web server, auto-scaling app server, and then we have a DB server. And here is how we collected the data at the bottom, right? So for the first, what we do is we run a VM, right? We run it for a period of time. Let's imagine that's 1 hour, okay? In this particular case, I think it's 30 minutes is the visualization you see here. So imagine you're running it for 30 minutes. For the first 15 minutes, you run the VM in clean phase, right? So there's no malware in that VM. So we run it in clean phase. We collect a sample every few seconds, right? And what we do is after minute 15, so here is every 10 seconds, we collect for 100 different processes, 28 different features for the first 15 minutes. After 15 minutes, we have a whole bunch of malware from VirusTotal. And what we do is we take that malware, we inject it into this machine, and then we start collecting for another 15 minutes. Essentially, we want to induce process behavior, right? So essentially, for each process, we want to see if there is a change in the features that it actually uses. And we do this across many, many different malwares. In this particular experimentation, we did 25. In the subsequent paper, we did a lot more injections. And we collect all this data. And essentially, we had a few million different samples, right? So we have, I think, 5 million unique samples of these data. And essentially, what we do is now we then we build a model. Once again, we did a 3D model versus a 2D model. So that is essentially this picture here, right? So if you just did this, that's 2D. If you collected a bunch of samples over time, then it becomes 3D. And we find that 3D performance is significantly better. And of course, understandably, if the window size increases, which is the size of the cube, right? One of the axes, the time axis in the cube. If that increases, then the performance accuracy is a lot better. Okay, so a lot more details in the paper if you're interested. In the interest of time, I'm gonna skip through to the final part of the talk, all right? Questions? Okay. All right, so let's now look at multiple VMs, right? So which is where auto-scaling comes into picture, right? So what we are now going to do is to analyze white box level features across a single tier, which is what makes it cloud specific, because you have auto-scaling of those VMs. So now we're going to compare behavior across VMs, right? So here is the first part of the work where we do not compare. We just look at a sample from across various time, right? We collect single samples. We call this single VM. So look at single VM. This is what we did previously, right? So essentially, it's a summary of what we did. So you collect single samples over time, and then you analyze and you train the model. But now, so if you think about it architecturally, what we do is here is VM0, right, on the left column, right? Sorry, the top row. And then the bottom row is VM1, and then the next one is VM, et cetera, VMN, and we collect it over time, right? So each row is time series, and we collect it over time, and then we build a CNN, we train a model on this data as though these data samples are independent. Right? There is no correlation between these samples. And then we perform prediction. That is essentially what we did previously in the previous work. Now, one of my students got this interesting idea of, well, before I go there, maybe I'll mention this one. So here's an interesting study that he did. So on the left-hand side, he did a study of, x-axis is time, and the y-axis is context switches for a given process. The number of times a process switches context, right? And so he studied a particular process for 30 minutes, and he ran the same thing for 2 times, right? So he created a VM, he studied the context switch for 30 minutes for a single process, and then he shut down the VM, created another VM again, and then for the same process he studied. And he found that, well, it's just random, right? So there's just some kind of fluctuation on the number of context switches over time. But here is on the right-hand side, when he did the number of voluntary context switches over 30 minutes for a single run, but for 10 parallel VMs, right? Which is an auto-scale VM, imagine. So you have 10 different VMs running in parallel, working with the same kind of workload. And he did 30 minutes of context switches, and bingo, and in one of those VMs, he injected some kind of malware, okay? And bingo, there you see, so this red spike shows that for one of those VMs that had the malware, there is some kind of interesting behavior there. So its number of context switches, you can see for all the remaining 9 VMs here, it follows a single curve, a nice curve here, but for one of those VMs at some point in time, it changes. So therein lies the question. So we want to see if we can correlate behaviors of VMs across over time, okay? And he got this idea of pairing samples essentially from Quora, right? So graduate student, he was writing code, he was consulting this online service called Quora. You might be familiar, very much like Stack Overflow. You have question and answers. What one of the biggest problem they deal with? Duplicate questions, right? So you have you ask one question, and then there is another person asking the same question, and they get into different forums and they answer these same questions, right, in a different way, and then they're distributed across their servers, and it makes it very hard for them. And nowadays you see that they combine these threads together, right? So the way they do that is the key question they're trying to answer is, given two different questions, are they the same question, right? So what he's trying to do here is, given two different samples, are they both malicious or are they both benign? That is essentially what he's trying to do. So he's trying to pair different samples across VMs. So on the top, you see VM0. It's the same architecture here, layout of various samples. In the middle, you see VM1, et cetera, and on the bottom, you see VMM over time, right? X-axis is the time. And what he does is he pairs different samples across these VMs and labels them as a single sample to indicate that they are both either malicious or both either benign, right? And thereby, he is correlating samples across multiple VMs instead of just one VM, right? So instead of feeding just one sample at a time, he's correlating a bunch of samples across multiple VMs at a single point in time that is processing the similar kind of workload, and thereby is able to correlate them. And then he paired them together and different kinds of pairings, right? So VM0 and VM1, and maybe VM0 and VM2, et cetera, different all kinds of pairings that he could perform. And he found that when you pair them, the results are significantly improved. And he found that this is, on the left-hand side is the single sample, where the samples are not correlated in a VM. On the right-hand side, you see paired samples, where the samples are paired together and correlated across different VMs that are auto scaling. And he found that when you pair them and then you build a model for it, the performance detection ability is much, much better. Okay, and that was very interesting result that he had. Okay, I think I'm close to time. So what I'm going to do is to give you some concluding thoughts on where we are going with this research. Okay, so there's all kinds of interesting directions. There are 4 different papers on this topic so far over the last 3 years, but that is just the beginning, right? So this is just meant to be, there's all kinds of interesting questions that arise, and one interesting direction, obviously, is natural extension to this, right? So we want to explore, right now we only explore infrastructure as a service cloud, so virtual resources, but there are all kinds of interesting architectures and clouds out there. So you can have containers in a cloud, right? So when you're dealing with containers, can we then apply similar techniques for a container, right? So you have multiple containers, and can we look at similarity across containers and put them in clusters or measure different kinds of metrics and see if there's malicious behavior? We also want to this goes to the Risha's question was, we want to actually make it more adaptive, right? So we don't want to be in black box, we don't want to be in white box all the time. We want, if there is some kind of flag that gets raised in the system, we want to be in black box mode most of the time. And if something, you catch something, and then immediately you accelerate and do the introspection, right? So you start looking at white box. Or maybe you do some shallow white box introspection, and when you see some kind of triggering event, you start to inspect a lot more carefully, right? So we want to do this a lot more dynamically. We want to bridge these 3 works in a much more dynamic and adaptive manner. That's an interesting direction we want to explore. And of course, I'm sure some of you have noticed the 3rd bullet point. That is one of the key issues, right? We didn't bother to look at that. If you have simultaneous attacks across multiple VMs, what's going to happen, right? So there is an assumption so far that, if an attacker attacks one VM, I can base the performance and the characteristics of remaining 9 VMs, right, to establish what is the normal behavior, right? What if, let's say, 5 of those VMs have been compromised simultaneously? Now you do not have a normal behavior. You have 5 VMs exhibiting one behavior, and now you have another 5 VMs that are exhibiting a different behavior, which is good behavior, right? You don't know. And there's lots of interesting theoretical results in this arena when you have, how do you, Leslie Lamport has some, when you're dealing with microprocessors, there's some work on figuring out whether a computation is correct or not when you're doing space travel, et cetera, right? So there's a lot of interesting work in finding out, majority may not be always good, right? So essentially, we want to explore some techniques from there. What is more interesting is some end-to-end automation, right? So we want to do some, one of my students currently is working on this topic, which is what we call as automated cyber threat intelligence detection, sharing, and response, right? So we want to do detection, we want to do sharing, and we want to do response. So imagine a cloud, we have multiple customers, you have Netflix, you have Dropbox, you have et cetera, right? So all of these customers are running a whole bunch of workload on this cloud. Now, if each one is doing independently, right, the chances of detection is going to be much more diminished than if there is some kind of combined way to do it, right? If there is a way to automatically detect and share certain kinds of cyber threats with other organizations, and you can do much better detection and response. And that is essentially an initiative that DHS and others started to come up with for information sharing across. This is for non-cloud computing situation. But essentially, they came up with this simple framework, what they call a STIX taxi. Essentially, STIX is, you can see at the bottom left, there is an example of what a STIX is. Essentially, it's a structured language for cyber threat. That's intelligence, okay. Cyber threat intelligence, right? So essentially, you can make a machine readable, imagine this is a JSON or an XML file that says, here is the attacker, here is what we know about the attacker, right? So you can make a very, very structured machine readable way to express a particular kind of a threat. We call it threat intelligence. And once you do that, you can actually transport it across different customers in the cloud, right? So you can establish a shared repository where your organization shares your sticks, if you will, with my organization and vice versa. We can establish certain kind of access control on who gets access to what. And once we do that, we can actually perform much more holistic cloud level detection. And once we detect, we can actually also automate certain kinds of responses. And one of the interesting response that we are exploring right now is, imagine there is a DDoS attack on your web server, right? If you detect a DDoS attack, we could respond by adjusting our auto-scaling parameters, right? What does DDoS do? It essentially kills a VM, right? It just overwhelms a single or bunch of VMs. Then what we could do is try to fight through it by now accelerating our auto-scaling capability, right? So we can just now scale out like 100 VMs, right, in random fashion. So it's going to be difficult for the attacker to attack all of those at the same time. Of course, it's going to cost you more, but at least you will survive the attack, right? So that's an example of how we can actually use the automated threat detection and sharing mechanisms for effective response. You can even do very simple things. You know, Dr. Greg White at UTSA, he told me sometimes even an email to the administrator will suffice, right? So if you can just send out, you know, if you can actually notify these people that there is something going on in an automated fashion, right? There's no human coming in and figuring out, I have to email all the employees, hey, there is a phishing attack that's going on in this organization. Send it out, right? Send it out to inform everybody else so they could take some precautions. So we could do those kinds of very simple things to actually for effective response, right? So that's an ongoing project that we are doing right now. And this is an example architecture. I'm not going to go over this, of course, but this is an example architecture that my student has deployed it on OpenStack, right? Essentially, you have the three components. You have the detection component that I just talked about in the previous three parts. We have the sharing component, right? So the detection component is the green, the sharing component is the red. I'm sorry, the taxi here, the black, and then the response component is the red, right? So he has integrated this as part of the actual OpenStack core, where you can now simulate different kinds of tenants, and you can actually share sticks and then respond in an effective manner, right? So very early stages, but I just wanted to, you can see we published in a conference last year, very early stage work, but something that's interesting that we are going to pursue. All right.
Now there are perfect timing, I guess. There were a few questions in the chat.
Sure.
So,
thank you, by the way. Okay.
Thank you so much. Samir, do you want to ask the question yourself?
Hello.
Hi, Samir.
Hello, sir. So I just wanted to ask a small question.
I didn't plant him. He is my student, by the way, but I didn't plant him there.
No, my research is on. But I just wanted to ask a small question. I'm not sure which slide it was, probably about 4 or 5 slides back. It was on the pairing part, yeah.
Yeah.
So instead of the, I just wanted to ask, like, instead of the pairs, would it be better if we calculate like a power set of VMs or even more than 2 VMs?
Absolutely, and we thought about that. And the problem is you have the explosion. You know, power set is exponential, right?
Yes, sir.
So we have an explosion. So what level of pairing, what should be the group size, right? So should we pair 2 VM samples or multiple VMs? It becomes very hard. And of course we settle with 2, you know,
yes, sir.
just a pair. But I'm sure it will be interesting experimentation, right? So if you have, let's say 10 VMs, you have 2 power 10 possible ways you can group them.
Yes, sir.
Each sample. Right?
Yes, sir.
It's crazy. So think about it. You're collecting, I don't know how many, right? So I think I had the number here. every 10 seconds across 100 processes for all of your tenants, for all the VMs, hundreds of thousands of VMs running on Amazon Cloud. Right?
Yeah.
It's
You
crazy.
probably need a supercomputer or something.
Yeah, at some point you have to balance the cost versus the
Yes, sir.
technology. And yeah, so it's an interesting problem to look into.
Yes, sir. Thank you, sir.
Yeah.
Thank you. The next question was from Luis. You want to ask the question?
Hi, Louis.
I think he's still muted. Why don't I go ahead and ask the question for him?
Sure.
Have you considered stick for graphical representation for the sticks? TIG, I guess, for the, right there, you have sticks, right? So have you considered stick for graphical representation?
I'm not sure what is that representation? Stick graphical representation?
So instead of taxi that is used here, have you considered stick for graphical representation? That was the question, I guess.
I'm not sure I understand that very well. Basically, the sticks here, this is not meant to be a graph. This is just a graphical visual of what this is supposed to be. But internally, this is not graphical. This is essentially a JSON document that connects, that has cross-referenced various different aspects of a particular threat. Imagine you find a ransomware threat in your organization. So sticks is focused, gives you a language to express that threat. So this is an attacker based in country X, right? So that's a threat actor. And that there is a campaign behind it, right? There is a campaign to get some presidential candidate elected. I'm not going to get controversial here, and then there is some indicators and there's some vulnerability that they exploited in your organization, right? So that is what we are talking about when you're talking about a sticks here. And once you can represent that, then you can share it with other organizations, and now they have a fingerprint to go search for, right? They know what to look for, and they can see if they have a similar vulnerability in their organization. This is not my idea. This is the US Department of Homeland Security's idea.
Yeah, I think he further clarified, but maybe this could be an offline discussion, but stick with G, STIG, is another software to graphically represent CTI with sticks language.
Oh, I think I know what you, okay, yeah, possibly, yeah. So we started with sticks taxi. When we started, that was sort of early stage. This is many years ago. And when this is on a different piece of work, and because we had some familiarity with this work, we stuck with it. And of course, there are many other ways we can actually capture cyber threat intelligence information, and there's some works in that area. Yeah, I'm not sure which will give you better results. It's unclear right now.
Okay, thank you. Murtuza, you want to go next?
Hey, Murtuza.
Hey, Ram, how are you doing? Great talk. This is the first time after 2 years or maybe more, I actually got to formally listen to what you're doing.
Oh, yeah. Some repetition, I assume, because my student defended at that time. Right?
Yes. But thank you for the very interesting talk. So let me kind of maybe pose the questions two ways. And the first question is alluding to my previous comment I made. I'm just trying to understand maybe how, so as you know, obviously, machine learning has been used in malware detection in a host setting for maybe over a couple of decades now. And so how have the features in, for example, such a cloud setting significantly different to kind of, or how is the entire setting of using machine learning significantly different? So what are the new insights specifically from the host-based scenario that basically we can see in your research? That was something that again, I'm coming completely from a person who has not done work in this area, so from an outsider perspective. And the second question is, you train, and the way I've understood is, if you train, so your models are nothing but the classifiers, basically, effectively, that differentiate between malicious executions to normal executions, right? So how generalizable are these models across multiple malwares, or do you need to train a different model for every malware? And so, yeah.
Right. So maybe I'll start with the second question then. It's something I remember now. So yeah, so no, the whole idea here is to try and refrain from that. Of course, there are certain malwares we will not be able to detect, like zero-day attacks that we have never seen before, ever, etc. But if you have some interesting behavior, so what we do here is we collect samples across, this is just a simple experimentation here, but we train samples across a whole bunch of malware, right? So we collect maybe, let's say 100 different malwares of different types, essentially. You get representations from different types of malware that are out there. And then you collect samples over a long period of time. You collect millions of these samples that represents all kinds of interactions among processes. And then we are trying to see whether if some other malware that has not been seen before, are we able to actually detect it, right? So essentially, we do not have to train. Of course, if you have a malware that is completely different from what the model has ever seen, right? We have to use different techniques in machine learning, such as maybe we have to generate some samples, like we can use GANs and etc. So we didn't go there, right? So right now, what we did was we only inject certain number of malwares, and then we see whether we can learn from it, and we can actually, as subsequently, one of the things we want to do is to use GANs to extend that behavior. Make sense?
Yeah, yeah. So the reason I'm asking is it's kind of a very challenging problem. Obviously, the goal would be to build a kind of a God model, right?
Yeah.
Which basically is able to obviously identify any malware that is possible. But obviously, we know the challenges that come with that. And I think obviously that would be not only a good I would say mix of choosing the right set of features, but also obviously choosing the right set of models actually. And it's not an easy task, but I think eventually that is hopefully where we want to reach.
I mean, we know from Computer Security 101 that a virus is just another computer program.
Exactly.
Right?
Yeah.
So the theoretical result is it's undecidable whether a given program is a malicious.
Yes, absolutely.
This is known to be, I mean, that's a death sentence for this line of work, essentially, right? So you cannot tell for sure. So all we can hope is, given some known good behaviors and known bad behaviors, can we still, try and find as much as we can, right?
Right.
The best of our ability. That's essentially what we're trying to do here. Now, going back to your first question, so what makes, I think this came out, and I think I apologize because I didn't make it very clear. So what gives cloud an interesting, the characteristics in a cloud, an interesting edge in malware detection? And there is one important thing we use, which is illustrated in this picture, right? So the picture on the right shows, you see different colors on the bottom. Each one is number of context switches we collect from that particular VM at that particular time. Right? So we look at a particular process, and then we see across, let's say 10 different VMs, right? So in this particular, 10 VMs for 30 minutes. Over 30 minutes, we find out how many times that particular process switches context, right? And you see that all the way they are switching similarly, right? So 9 of those VMs are switching almost the same over time. When there is auto scaling, remember? So we're talking about auto scaling VMs. And at minute 15, roughly, there is one VM where that particular process switches in a very different way, right? And this is meant to be an extreme example. So obviously it doesn't happen like this. It's not as exaggerated as this, right? You're talking about multi-dimensional graph and vector and so on. But you get the point here is that when you have multiple VMs that are scaling in and out, and what we're trying to do is observe similarity of behavior across those VMs. Right? So it's a much more dynamic way of looking at the system. And that is one of the key characteristics of cloud, right? So when you have a specific auto-scaling tier, we can observe similarity of behavior across those VMs in that tier, which is not common in typical single VM level work. Over there, all we do is we look at some binary analysis of the code of that particular VM. We don't see dynamic differences in the behavior across multiple VMs, right?
Interesting. Yeah. Absolutely.
And we could do this for switches, network switches. We could do this for all other kinds of resources in the cloud,
Perfect. Thank you. Thank you very much for the clarification, Ram.
Thanks.
Yeah. Thank you so much, Ram, for giving a great talk. I think it was a very good introduction to this research. I think I understood the field a lot better now, I guess, the problem scope, and I'm sure everybody's appreciative of that. And as I mentioned, Ram is leading the Trustworthy AI within the Matrix Consortium. So if anybody is interested in working further with him on these problems, feel free to reach out to him. And
Absolutely. I'm hiring, so any student interested, for sure. Thanks for the opportunity, and thanks to everyone for listening in.
Yeah, thank you, and we'll see you next week. Bye.
Thank you. Bye.